Okay, I'm going to get started. Hope you can all hear me okay. Today's class, we're going to move on from discussing the electrical force between electrical charges to actually calculate and explore the electrical field that's created by electrical charges. And the bottom line is that electrical forces between electrical charges are conveyed by or carried by, mediated by something we call the electrical field. And today's class is all about the electrical field. So there's a few things I'd like to go through today, and I've listed them. So I want to first introduce just the concept of the electrical field and the definition of the electrical field. That's really going to be our first task for today. This guy here. I want to then look at some examples or illustrations of computing, calculating electrical fields of charge arrangements. That's this guy here. I want to look at how we sketch or draw electrical fields of charge arrangements using field lines. That's this item here. And then I finally want to end up with some remarks on electrical fields and electrical conductors. And that's this topic here. So that's basically the plan for today. We'll work through these items. So let's start with idea, concept of electrical field, and then definition, kind of a precise definition of the electrical field. So the electrical force, when it was first understood, there was a mystery, a real mystery associated with electrical force. And the mystery was that was a force between electrical charges at some distance. And the mystery was this action or this force at some distance between separated charges, between distance charges. It was actually like, as a mystery puzzle associated with a gravitational force. So the gravitational force is a force between masses, separated masses, distance masses. And so that's also an action at a distance force. And it was a mystery how that worked. And the electrical force, that action at a distance, was perhaps a mystery or a big mystery. And the gravitational force, that force between masses, was perhaps a big mystery, because the everyday forces that scientists or people knew were actually contact forces, where things had to touch, things had to be in contact for those forces to be exerted, for those forces to be experienced. So if you think about friction, the friction forces, you need two surfaces in contact. You need contact. For tension force, you need contact between you and the string, you and the cable, you and the rope. Those everyday forces all involve contact between objects, between us and objects, whereas electrical force is some strange action between charges that are separated. Gravitational force is some strange action between masses that are separated. So that was a real puzzle. And basically, these laws for electrical forces, these laws for gravitational forces were kind of, I would describe them on a kind of shaky foundation at the time, because they were laws, they were equations for gravitational and electrical forces, but how those gravitational electrical forces were communicated, transmitted, was not known, was completely unknown, was a complete mystery, was a complete puzzle. Well, the solution to the puzzle came from a very famous physicist, chemist. You might know his name from chemistry. You might not know his name from chemistry. His name was Michael Faraday. He had an interesting history because he was not trained in science. He had no sort of science mathematical education, but he was actually one of the most sort of influential scientists of the 18th century. And he came up with the idea, came up with a thought that the electrical force between electrical charges and also the gravitational force between masses, those forces are actually transmitted or carried by quantities called fields. Now, fields you can't see, fields you can't feel, or fields you can't taste, but transmitting the electrical forces between electrical charges or transmitting the gravitational forces between masses are these unseen, unfelt forces that the charges themselves experience, the masses themselves experience in the electrical and gravitational cases. And so that was a brand new idea. So with that idea, kind of solve this problem of how did one charge experience the force of the other charge? How did one mass experience the force of the other mass? Those forces were being transmitted, conveyed, carried by fields. So to say nowadays, we understand that between charges is a kind of invisible messenger called the electrical field transmitting the electrical force. And we give that the symbol, here's the symbol for that electrical field. And we also nowadays understand that between masses, there is a gravitational field. And that gravitational field, we give it the symbol G here, that's conveying or transmitting the gravitational force. And actually, one thing that's really quite interesting is that nowadays, we understand, you know, those contact forces I mentioned, so the frictional force where two surfaces had to be in contact, the tension force where you and the rope, you and the cable had to be in contact. We actually now understand that those forces are really action at a distance electric forces. Action at a distance electric forces between the atoms and molecules of the two materials in contact. So if you slide a book across a desk, the atoms, molecules of the book and the atoms and molecules of the desk, they experience electrical forces that are transmitted by electrical fields. If you pull on a rope or a cable, the atoms and molecules of you and the atoms and molecules of the rope or the cable, they experience electrical forces that are transmitted by electrical fields. So at its heart, the friction force is an electrical force, an action at a distance force. At its heart, the tension force is an electrical force, an action at a distance force. Okay, so this slide tells us precisely, exactly, how we define the electrical field, the definition of the electrical field. And so to imagine the definition of the electrical field, I'm going to ask you to imagine two charges. So one charge over here, charge on the left on my sketch, that's what we're going to call the source charge. And the other charge over here on the right, that's what we're going to call the test charge. And by source charge, we mean that's the charge that we're thinking about, which could be charges that we're thinking about, that are creating a surrounding an electrical field that fills up the neighborhood of those source charges or that source charge. And then the test charge is a little different. It's a charge that we take, we put in this field, and we use that test charge to probe that electrical field, to basically determine or measure that electrical field. And so that's the test charge. Now, on this sketch, I've called Q the source charge that's producing the electrical field, and I called Q subscript naught the test charge that's probing that electrical field. And so that's just a, just a little bit of notation. Okay, so given that explanation, here's how we define the field. The electrical field at the location of the test charge is defined as the force on the test charge, so that's this F here, divided by the charge of the test charge. And that ratio of the force that's experienced by the test charge divided by the charge that's owned by the test charge, that defines the electrical field at the location of the test charge. And so you can see in that way we can use that test charge to explore the electrical field. We could walk around this neighborhood in the neighborhood of the source charge and measure the force on the test charge. And knowing the charge of the test charge, we could map out, we could explore the electrical field. The equation here, this what we call, this is a field equation, the field equation for the electrical field. It's really the equation that defines this abstract quantity, the electrical field, in terms of things, in terms of quantities that we're more familiar with, in terms of quantities, in terms of things that are more measurable. We can measure the force in newtons that's experienced by the test charge. We can measure the charge in coulombs that's owned by the test charge. In that way, by dividing that force in newtons by that charge in coulombs, we can calculate the electrical field in newtons per coulomb at the location of the test charge. Now, there is one little point here that when you think about a test charge probing the field of the source charge, you want to think about the test charge as being much smaller than the source charge. In that way, the test charge doesn't perturb the source charge or perturb the electrical field. And so that's this little comment down here. Okay, so that's the idea of fields. Fields are things that carry forces, and the definitions of the electrical field. There's a field equation defining the electrical field in terms of the force on a test charge. Now I want to look at some examples of electrical fields. And I'm going to start with the electrical fields of single point charges. And so that's what I've sketched here. So this overhead is the electrical field B of a positive point charge. And down here on the bottom left, here's the positive point charge. And upstairs here on the right is a test charge, Q naught, that's located at some point that I called P. Now, I'm going to start calling that the field point. It's where we're interested in the field. It's where we're exploring the field. It's where we're kind of probing the field with the test charge. To write down what the electrical field is of the single positive point charge, all I'm going to do is take this field equation. Here it is. That the electrical field at that location is the force on the test charge divided by the test of the test charge. That's F over Q naught. And then I'm just going to fill in, I do it here, Coulomb's law for the force between these 2 point charges, the source charge and the test charge. So Coulomb's law says that the force is simply the Coulomb constant, the force constant, times the product of the sizes of the 2 charges, so that's Q and Q naught, divided by the square of the distance separating the two charges. That's this r here. When I do that, I see that the charge of the test charge, that's the Q naught, actually cancels out. From the numerator and denominator. And we're left with this equation here. This is the equation for the size of the field, the strength of the field, the magnitude of the field of a point charge. It's the Coulomb constant times the size of the charge divided by the square of your distance from the charge. So a bigger charge will create a larger surrounding electrical field. A smaller charge will create a smaller surrounding electrical field. As you increase the distance from your charge, the field falls off, the field decreases as an inverse square law. And so that's the equation. This is an important equation. We'll use it a lot as a building block. It's the equation for the electrical field of this point charge. Now, for a positive point charge, the field is defined as if the test charge was positive. So if you've got a positive source charge and a positive test charge, then there's a repulsive force between the source charge and the test charge. Therefore, the force is radially outwards from the source charge, as I've pictured here. And therefore, the field is radially outwards from a positive charge. So the direction of the field is away from the positive charge. Well, this is an important building block to know the field that's created by a single positive charge. Let's look at the field that's created by a single negative charge. Let's compare that as another important building block. And so that's this slide. This is the electrical field of a negative point charge. So again, I could figure this electrical field of a negative point charge, again using the field equation. And that's what I've pictured on this slide. I've imagined, again, put in the source charge, it's negative now, over here on the bottom left, putting my test charge, positive test charge, up here on the top right. They're separated by some distance r. And then I can write the electrical field at the location of the test charge at what I'm calling the field point. I can write it using that definition, that field equation. So the electrical field is the force on the test charge divided by the charge of the test charge. I can again fill in Coulomb's law for the force between these pair of point charges, the source charge and the test charge. The size of the force is K, Coulomb constant, times the product of the two charges, so it's Q and Q naught, divided by the square of the distance between the charges. Again, we see, right, that the Q naughts, the test charge cancels out in the numerator and denominator. It really doesn't matter, whether the test charge is a nanocoulomb or 2 nanocoulombs or 3 nanocoulombs. If it's as big a test charge, it experiences bigger force. And when you calculate the field, the bigger force cancels with the bigger charge. And so we find here an expression for the size of the electrical field of a negative point charge. Again, it has the same formula as positive point charge, just depends on the Coulomb constant, the amount of charge, and the square of the distance from the charge. So just like the positive charge, if you've got a bigger negative charge, it's going to create a surrounding bigger electrical field. If you're further from the negative charge, the field's going to be smaller as an inverse square law. The only difference is that now, look at the test charge and the source charge. Now they're opposite charges, so the forces are attractive, and so the field points in the opposite direction towards it. The field is going to push the test charge towards the source charge, so it's radially inwards towards the negative charge. And so that's the second big building block that we need. Okay, so now with those building blocks of the fields of point charges, positive point charges, negative charges, we're gonna switch to looking at some example problems and exploring more complicated electrical fields of more complicated arrangements of charges. Here's an example problem. And in this problem, I'm just going to calculate or compute the magnitude of an electrical field and the direction of an electrical field that a point charge is immersed in using the field equation. So this problem is an example of the field equation. And what we're told in this problem is that we've got an object. It has a certain mass, 3.8 grams. It has a certain charge, minus 18 microcoulombs. And it's suspended in midair. It's suspended in midair in an electrical field, in a uniform electrical field that we've somehow created. We've somehow manufactured this uniform electrical field. And our job, given that this object with a given mass and a given charge is suspended in midair, at rest and staying at rest, we've got to figure out what the electrical field is, what the size direction of the electrical field is. So let's go ahead and do this. I think I might try this on the whiteboard. Okay, so I think I've shared my whiteboard with you, and we're going to work out this problem. So let me start with a little sketch. I always like to start with a sketch. Here's the test charge. And we know the mass of the test charge. It was 3.6 grams. That's 0.0036 kilograms. And we know the 3.8 grams, sorry. And we know the charge of the test charge. It's minus 18 microcoulombs. So that's the information we know about the charge itself. We know that it's floating in space. And it's floating in space because there's an equilibrium of two forces on the test charge. Actually, what's happening is that gravity is pulling the test charge downwards. So here's the force of gravity. And it must be that if the charge is floating there, that the electrical force is pushing the charge vertically upwards. Again, if it's in equilibrium, if it's at rest, staying at rest, it must be that the sum of these two forces, so gravitational force vertically downwards and electrical force vertically upwards, their vector sum must be 0. Otherwise, the charge would move, the charge would accelerate, but the charge is at rest and staying at rest, so the sum of the forces must be 0. That means that in this simple case, right, it must be that the electric force, gravitational force have the same sizes, but they have opposite directions. That's the only way we can add those two forces up so that they cancel one another out. I'm just finally looking at chat, Zoom chat, and I've seen a couple of questions. So let me answer those. From Clayton, so essentially contact forces have visible messengers. Contact forces like tension forces or friction forces, they're not visible messengers. There is electrical fields between the two surfaces in contact, between the objects in contact. And those invisible electrical fields are conveying the forces. Just like, you know, if you had two separated charges or two separated masses, invisible electrical gravitational forces are conveying the forces. Do you always assume test charge is positive? From Tyler. That's actually a good question. So I took the test charge as positive. And you can think of that as a convention for defining the electrical field. We define the electrical field as in terms of a positive test charge, which means that the electrical field points away from positive charges and towards negative charges. We could have defined the electrical field in terms of a negative test charge. Then the electrical field would point towards a positive charge and away from a negative charge, but nobody ever does that. So it would be very confusing. So we do assume, we do make the choice that the test charge for defining the electrical field is a positive test charge. So that was a very good question. Okay, so back to this problem. We figured that the gravitational force and electrical force are equal and opposite. Now we need to figure out, what we're going to do is figure out the electrical force, and then we can figure out the electrical field that creates that electrical force. So we'll start by figuring out the gravitational force in this problem. It's just the mass of the object, we know that, times the acceleration of gravity, we know that. So this is 0.0038 kilograms times 9.8 meters per second squared. That comes out to be, I worked it out ahead of time, 0.037 newtons. And that actually means that the electrical field must also be 0.37 newtons if these two forces are equal and opposite. And so this over here on the left-hand side here, this is kind of an analysis of the forces involved. And we now know that this equilibrium of the charge as it floats in air is due to these equal and opposite electric and gravitational forces of 0.037 newtons. Now we can go ahead and calculate the field itself. Let's start with the size. The field, from the field equation, is the force divided by the charge. The electrical force divided by the electric charge. Well, we know the electrical force is 0.037 newtons. We know the charge is 18 times 10 to the minus 6 coulombs. And if I divide one by the other, I just got to look this up because I figured this out, but I've forgotten it. What was the answer? This is minus 2,090 newtons per coulomb. So that's the electrical field. That's the strength of the electrical field. What does the minus sign here mean? Well, the minus sign means that the electrical field is in the opposite direction to the electrical force. So the electrical field here is a vector, it has a direction. The force is a vector, it has a direction. The charge is not, it's a scalar. It can have a sign, but it doesn't have a direction. If the charge is positive, E and F are in the same direction. If the charge is negative, E and F are in opposite directions. So this sign here means that the electrical field is opposite the direction of the electrical force. Fe, the electrical force, was up. It must mean that the electrical field is down. And so that's the answer to the field on this side. Okay. I'm looking in chat again. So there's a question, would FG be negative? Would FG be negative? You could set up this problem so that downwards is negative, in which case, if you wanted to write the size and direction of FG, then FG would be negative and FE would be positive. Or you could take the alternative convention that downwards is positive and upwards is negative. So in my convention, let's see what I've done. In my convention, well, maybe the best answer to this, here I've just written down the size. These are just the sizes. The sizes of these two are equal. The directions are definitely opposite. So if you wanted to include the direction, I did it with the arrows rather than plus or minus signs. We would indicate that one is plus or minus, but this, just to be clear, I just calculated the size here, and I calculated the size here. I started to worry about the direction over here. And what I learned here about the direction was this minus sign just told me that the electrical field is in the opposite direction of the electrical force. And since I knew that the electrical force was up, it meant that the electrical field was downward. So I hope that's okay on the directions. What does direction of the electrical field mean in terms of towards or away from the source charge? Yeah, that's an interesting question in this problem, because I didn't tell you how we made the uniform electrical field. So there must be charges somewhere else, a distribution, an arrangement of charges somewhere else that produce the electrical field. But I'm actually going to come back. I won't answer that completely now. How would you produce a uniform electrical field? I'll show you that a little bit later. Okay. I got a quiz question. Okay, let me give you the answers to the quiz question. And if you got any questions after that, just stick them in the chat.
Yeah, my vehicle has.
So the forces between these two charges, the force experienced by Q1 and the force experienced by Q2, those, for example, by Newton's third law, they must be equal in size, opposite in direction. They're a force pair. So if I were to draw the forces on Q1 and Q2, I'll imagine they're the same, same sign charge. I've got to go back here. If I would draw the forces on Q1 and Q2, they might look something like this. Equal size forces, oppositely directed forces. And that's because these are a pair of interacting charges. And when they interact, they exert equal and opposite forces on one another. So the force sizes are the same. The fields, on the other hand, charge Q2 is bigger. It creates a bigger electrical field. So its field would be bigger than the field created by charge Q1. That creates a smaller electrical field. And so the fields are not the same. Now, the bigger charge is sitting in a smaller field. The product of the charge and field makes the same force as the smaller charge sitting in the bigger field. So you get the same forces on the two charges, but you get different fields at the locations of the two charges. It's the same situation as if you imagine the force between you and the Earth, gravitational force between you and the Earth. So you and the Earth both experience the same size gravitational forces. Your force on the Earth and the Earth's force on you are the same size. But the gravitational field of the Earth at your location is much bigger because the Earth's much more massive. Your field at the location of the Earth is much smaller because your mass is much smaller. But when you come to multiplying your mass and the gravitational field, both you and the Earth get the same forces. So I hope that's clear. Okay, I want to say a little bit about superposition principle for electrical fields, because if we're going to have collections of point charges, we need to know how to superimpose the electrical fields. And so here's a picture of how this works. And this works very similar, works in the same way as superposition of electrical forces. This is just superposition of electrical fields. The net charge, the net field due to a arrangement of charges is simply the vector sum of the individual fields of those charges. So if you have two charges, for example, charge 1 and charge 2, then the resulting electrical field of the two charges is simply the electrical field of the first charge plus the electrical field of the second charge, remembering that these fields are vectors. So for example, I pictured it here in this little sketch. Here's charge number 1 down on the bottom left. And at this field point, I labeled it P, at this field point is creating an electrical field here, E1. Here's charge number 2 over here on the upstairs. And at this field point, it's creating an electrical field labeled E2. And you can see that Q1, charge 1, must be a positive charge as the field points away from it. Charge 2 must be a negative charge as the field is pointing towards it. But anyway, the total electrical field at this point P, at this field point P, is just the vector sum of E1 pointing up and towards the right and E2 pointing up and towards the left. That vector sum is here. And that's what I've called E. It's the sum of those two vectors. You can see how it's the sum of those two vectors. If I go on to the next slide, I've drawn the vector addition. So to picture the vector addition of the electrical field E1 and electrical field E2, to make the electrical field E, I sketch E1. Here it is. That's the field of the first charge. Oops. Got to go back here. I've sketched the electrical field of charge Q1. I've then drawn, starting at the tip of the electrical field of Q1, the electrical field of Q2. That's this second arrow here. And then the resulting vector, it runs from the tail of the first vector, E1, to the tip of the second vector, E2. And that's the resulting electrical field, E. And so this slide shows that vector addition. You could do that vector addition the other way around if you choose, adding E1 to E2. Let me just show you that. That's shown here. So in this slide, I do the vector addition by first sketching E2. That's the electrical field of the second charge. Then at the tip of E2, I draw the vector E1. That's the electrical field of the first charge. And then the resulting electrical field runs from the tail of the first vector to the tip of the second. And so this is the resulting electrical field. And that's, again, showing the vector addition of those two electrical fields. So that's superposition of fields. And it works the same way as superposition of forces. So let's look at a couple of examples. Of superposition of electrical fields. And this first example I want to look at, this involves the water molecule. Or, a water molecule is an example of this type of electrical field. So the water molecule H2O is famous as what we call an electrical dipole. So water molecule H2O it's overall electrically neutral, but it has a positive end to it and it has a negative end to it. So the positive end is the kind of the hydrogen atom end, and the negative end is the oxygen atom end. And I pictured that here. So here's a water molecule. And here's a hydrogen ion, here's a hydrogen ion, here's the oxygen ion. And negative end of the molecule is upstairs here. The positive end of the molecule is downstairs here. And so although it's electrically neutral, it does have separate negative and positive parts. And we call that arrangement of charge, we call that an electrical dipole. So an electrical dipole is something that overall is electrically neutral, but has a positive end and a negative end to it that is separated by some displacement, some distance. Now, the water molecule is famous because it has a very big electrical dipole. It's a very big electrical dipole. It's the reason that actually it forms a liquid. The water molecules attract one another. And it's the reason actually that it works very well as a solvent. So if you put salt in water, it pulls apart those sodium and chlorine ions that are stuck together, because one's positive and negative charges. Its electrical fields, the water's electrical fields, pulls apart those sodium and chlorine ions, and the sodium chloride dissolves in the water. That's how water is good as a solvent. What we're going to do as an example of superposition is actually calculate the electrical field of an electrical dipole. And so I'm trying to show you an electric dipole on this sketch here. Downstairs on the bottom of the sketch, here's a positive charge. And over here on the right, here's a negative charge. And they're separated by some distance here. And this distance is actually 2 times A. So A is the distance of the positive charge on the left of the vertical y-axis, and A is the distance of the negative charge on the right of the y-axis. And so the separation between these two charges is actually 2A. Now what we're going to do, and we're actually going to use both those equations for the fields of point charges and that principle of superposition for charges. We're going to calculate the electrical field, this point, field point P here. We want to know what this electrical field is. Now, that electrical field is made up of an electrical field that's created by the positive point charge down at the bottom here on the left, and the electrical field of the negative point charge from this negative point charge on the right here. And so the first thing in trying to understand and picture the resulting electrical field of this arrangement of charges is I sketched the individual fields, and then I looked at how those fields will superimpose, how they will add up to make a resulting electrical field. And so that's what I'm doing here. The positive charge has a field that points away from the positive charge. And so that's this upwards and to the right arrow here. That's E1. That's the electrical field of the positive charge over here. I called it Q1. And then downstairs here, pointing downwards and towards the right. That's the electrical field of the negative charge. I'm going to call that Q2. And the electrical field of a negative charge points towards the negative charge. So it's pointing towards that negative charge. So those are the two fields in this problem. And this, I'm going to explain it in a little more detail in a moment, is the resulting electrical field. It's the vector sum of E1 and E2. If I first draw E1 and then I draw on its head E2, I get this resulting electrical field. Or if I first drew E2 and then drew E1 standing on its head, I get this resulting horizontal electrical field. And so this is the resulting electrical field. And we're going to calculate the strength of that field. Now, to calculate the strength of it, I want to define some quantities. So A, as we mentioned, is the separation of the distance from the positive charge and the negative charge from the midplane here, this y-axis, vertical axis here. R, there's an R here and an R over here. That's the distance from the positive charge to the field point or the negative charge to the field point. And then you can see that A and R over here on the left and A and R over here on the right make up a kind of right angle triangle on both sides of the y-axis. And theta is the angle adjacent to the horizontal side in the right angle triangle. And this theta here is the same as this theta up here. This is also theta, and this theta here. And that's just a little bit of geometry that will help us as we solve this problem. Anyway, that's a sketch. It's a sketch of the charges, how they're laid out. It's a sketch of the resulting electrical fields of the individual charges. And it's a sketch of the resulting electrical field from the superposition of the two individual fields, E1 and E2. And all I'm going to do on the next slide or two is just calculate the strength, the size of this resulting electrical field. So let's go ahead and do that. Okay, so first step on this slide is I'm going to write down the fields E1 and E2. I'm going to write them down using the equations for the fields of point charges and write them down in X and Y component form. So I'll write them down in a form that tells me the electrical field in the X direction, the horizontal direction, the electrical field in the Y direction, the vertical direction. As I do this, my X is going to be towards the right, my Y is going to be vertically upwards. This is my little coordinate system. Okay, so let's start with the field E1 of the charge Q1. Here's Q1. Its magnitude or strength or size at the field point is the Coulomb constant divided by the size of the charge divided by the square of the distance, so KQ over R squared. If I want the X and Y component, so here's the X component and here's the Y component of E1. All I've got to do is imagine the right angle triangle that's made up of the vector E, that's the hypotenuse, E1, and then the horizontal side of the triangle is E1x. The vertical side of the triangle is E1y. And then I can just use geometry or trigonometry to figure out E1x, E1y from the magnitude of the field, the E1, the hypotenuse. So E1x is adjacent the angle theta. And so E1x is just the magnitude of the field times the cosine of theta. E1y is opposite the angle theta. And so E1y is just the strength of the field times the sine of the angle, because it's opposite. And so this is upstairs here. This is E1x and E1y for charge, the positive charge Q1. And then I'm going to do the same thing for the second charge. So here's the second charge. It's the negative charge. It's on the positive x-axis. Its charge is minus q. The strength of the field that's created by that charge at the field point is given by this equation here, kq over r squared. Depends on the amount of charge, square the distance, and the Coulomb constant. And again, I can think of a right-angled triangle. It's getting a little complicated in my diagram here, but it's made up of E2, the hypotenuse of the triangle, the long side of the triangle here, and E2x, the horizontal, and E2y, the vertical sides of the triangle. And I can use trigonometry for that right-angled triangle to write down E2x and E2y in terms of the magnitude of E2, kq squared q over r squared, times either cosine theta, if I want the horizontal, that's adjacent to the angle, or sine theta, if I want the vertical, that's opposite the angle. And I get the x and y components of the field of the second charge. Let me look in chat. You can also see the test chart. Oh yeah, that's an old question. So I'll leave that one for now. Okay, so now we're at a point where we've got, we've calculated the fields in x and y component form. So that's a big step. And the reason that we do that, as you know, is that it's then easy to add the fields to get the resulting field if you've got the individual fields in x and y component form. One thing I want to point out is the signs here. I put in the signs by hand by consulting the picture, by consulting the sketch. So E1x is to the right and E1y is upwards. Those are the positive directions, positive and positive. E2y is positive, but E2x is positive, but E2y is negative, it's downwards. So for the second field, the x component, horizontal component is positive, but the y component, the vertical component is negative. So that's important. I put in these signs by hand here. Okay, so now we got to add these two fields. And that's what I'm going to do on this side. So to get the total field, I can just add the x components of the individual fields to get the total x component. And I can add the y components of the individual fields to get the total y component. So Ex, that's the resulting x component, is the sum of E1x and E2x. Ey, that's the resulting y component. That's the sum of E1y and E2y. So I just filled in from the prior slide, I didn't write it all out, E1x and E2x. Now, E1x was kq over r squared times cosine theta, and E2x was actually the same thing, kq over r squared cosine theta. And so we just get this little expression here. Ey, that's the sum of E1y and E2y. E1y was kq r squared times sine theta. E2y was minus kq over r squared times sine theta. So these two components cancel out and we get a 0 here. And all that says is, if you look at the picture, the y components, the vertical components of these two individual fields have canceled each other out. One was up and one was down. But the x components of the fields, those are both in the same direction. So those are added together. And that's what our picture told us. The resulting field was from left to right. The up and down components of the fields have canceled each other out. And so this is the field in x and y component form. We can actually rewrite, that's all I did down here. I'm going to rewrite that field to learn an interesting thing or two. I rewrote this field by replacing cosine theta as adjacent over hypotenuse. So think of the right angle triangle down here. Here's the theta in this corner on the left. Here's the hypotenuse. Here's the adjacent. Cosine theta is adjacent over hypotenuse. So it's A over R. So I can replace the cosine theta with A over R. And I did that here. That's all I've done there. And we learned an interesting thing. The field of this arrangement of charge, a positive and negative charge, like a water molecules, positive and negative ends. That field drops off, not as 1 over r squared, not as 1 over the square of the distance from a positive charge, or 1 over the square of the distance from a negative charge. It drops off much more quickly. It drops off as 1 over r cubed. And that's because the fields of the positive charge and the negative charge are partially canceling one another. And what survives, what is left, is a field that goes as 1 over r cubed. So this is a really important point that applies to all electric dipole fields. That those fields fall off not as the square of the distance, like the field falls off from a single negative positive point charge, but it falls off as the cube of the distance, as 1 over r cubed. And then the second important point is that the strength of the field. Look in the numerator. There's a Q, there's a Q, and there's also actually a 2A. There's a 2 on the left and an A on the right. Q is the amount of charge on the positive or the negative end of the dipole. 2A is the separation between the positive and negative ends of the dipole. And so the field we discover is in proportion to the product of the amount of charge on the positive and negative ends times the separation between the charges on the positive and negative ends. So if you put more charge on the positive and negative ends, you get a bigger field. But if you separate more the positive and negative ends, you also get a bigger electrical field. We call that product of that distance times the amount of charge, we call that the dipole moment, the electrical dipole moment. And the field is in proportion to that electrical dipole moment. Okay. Well, that was one example of superposition. I got a second example in the slides. I'm not going to work through that. You might want to look at that sometime. But it was the same procedure. I want to turn in the last 15 minutes to how we draw field lines, how we sketch field lines, and how we sketch electrical fields, how we draw electrical fields, and we use what we call field lines. So here's an example of drawing field lines. This is the sketching the electrical field of a single positive charge. And we sketch it by drawing these lines, so these radial lines here coming outwards from that charge. And the magnitude of the field is represented by how closely packed the lines are. So look, here near the positive charge, the lines are closely packed. That means that's a strong electrical field. And here far from the electrical charge, the field lines are much more loosely packed. That's a weak electrical field. So the closeness or the separation of the field lines indicates the strength of the electrical field. And then the field's direction is just indicated by the direction of the field lines. And so this is the field of a single point charge. So, you know, as we know, the field is strong if you're close to the charge. So in here, where the field lines are densely packed, and the field is weak if you're far from the charge, out here where the field is much more loosely, field lines are more loosely packed. Over here on the left, the field points away from the charge. The field lines point away from the charge. Over here on the right, the field lines point away from the charge to the right, and that's where the field is away from the charge. And upstairs, right, the field lines point up because the field is up. Downstairs, the field lines point down because the field lines point down. Now, a couple of other remarks are that field lines always start on positive charges. So you see this charge is kind of the origin or the source of field lines. And that's what we think of positive charges as. They're the source of field lines. And also you'll notice that none of my field lines cross one another. Field lines can never cross one another in a sketch of electrical fields, in a drawing of electrical fields. Here's a corresponding electrical field for a negative charge, corresponding field lines for a negative charge. So this is the field lines of a negative charge. Again, just to stress, the density of the field lines, whether they're closely packed together or loosely packed together, indicates the strength, the size, the magnitude of the electric field. The direction of the field lines indicates the direction of the electrical field. So these are the two key things about drawing field lines that tell you the size of the electrical field and the direction, the orientation of the electrical field. So look, the electrical field near the negative charge is going to be strong. And you see here, the field lines are closely packed. So it is a strong electrical field. The electrical field far from the negative charge, outside here, that's going to be weak. And you see that the field lines are loosely packed out there, indicating that. The field of negative electrical charge points towards the negative electrical field charge. So these field lines, look, this one upstairs here points downwards towards the negative charge. This field line down here points upwards towards the negative electrical charge. The field line on the left points towards the right to the negative charge, and the field line on the right points towards the left, towards the negative charge. So those field lines are showing us where the field is strong, near the charge, showing us where the field is weak, far from the charge. They're showing us the direction of the field. It's downwards if you're above the charge. It's upwards if you're below the charge. It's to the right if you're on the left of the charge, and it's to the left if you're on the right of the charge. And again, these field lines never cross one another. They're not allowed to cross one another. Okay, this is the field of the electrical dipole. This is the field that we discussed in that last quantitative example. Let me just make a few remarks about this. So the electrical dipole is made of this positive charge. Oops. It's made of a positive charge over here on the left-hand side and a negative charge over here on the right-hand side. So this is our dipole arrangement. If you were close to the positive charge, or if you were close to the negative charge, what would the field look like? So supposing we're somewhere in the neighborhood of the positive charge, or somewhere in the neighborhood of the electrical charge. Well, then if you're much closer to one charge than the other charge, it just basically looks like the field of the nearby charge. So close to the positive charge, the field just looks like the field of a positive charge. The field lines come radially outwards. If you're close to the negative charge, the field looks just like the field of the negative charge. The field lines go radially inwards. So that's the field close to the charges. If you were far from both the charges, supposing we walked off the overhead upstairs over here, or we walked off the overhead downstairs here, there the field would look very weak. There would be very few field lines. And that's because this field of a positive and negative charge, we said it falls off not as the square of the distance, it falls off as the cube of the distance. So the field will get very weak over to the top left, top right, bottom left, bottom right, far from the charge distribution. At the midpoint, at the midplane between the two charges, this line here, you'll notice that the field just runs from the positive charge towards the negative charge. What's happening here is that the two fields of the two charges are superimposing, and they're superimposing in a way similar to our calculation. The horizontal components add up. The fields of the horizontal components add up, make a field from left to right. But the vertical components of the field of the positive charge and the vertical component of the field of the negative charge, they're canceling out. They cancel one another out. And so you get this field on the midplane, this characteristic field on the midplane that just sweeps from the left to the right. Okay, I wanted to show you, let's go back to that last slide. This is the dipole again. I wanted to just show you a demonstration of the electric dipole field. So let's take a look at that. And I'm going to share a different screen here. And so what you're seeing here is actually a film of oil in green in which there are tiny iron filings in the oil. And I'm going to immerse that field, that oil and filings, in an electrical field of an electrical dipole. And the two charges on the dipole, one of them's here, and one of them's just below my finger here. Here they are. So this is going to become positively charged, and this is going to become negatively charged, just like the overhead, with the positive charge on the left and the negative charge on the right. And I'm going to charge these up with a Van de Graaff generator that we've seen in class. And so I'm just going to play this video as I charge up the Van de Graaff generator, and I charge up this positive charge on the left and this negative charge on the right. You see, watch these iron filings. They're orientating and grouping to show us the electrical field. We're starting to see the pattern of the electrical field that emerges from these iron filings. And so, although we can't directly see an electrical field, we can use things like iron filings in oil to kind of image the electrical field. And I hope you can see here that sort of pattern of field lines that we saw in the overhead of the electrical field of an electrical dipole. I'm going to stop that there and go back to my slides. I'm going to show you one more electrical field.
You can answer the question in the chat real quick.
Oh yeah, sorry, my chat has gone. Let me see if I can get back to chat. Okay, so there's a question. The demo is going from right to left. So the right side is the positive one, or the is the iron negatively charged. Actually, you can't really tell in that demo which side is positive and negative. So it kind of maps out the pattern of field lines, but it doesn't really tell you which side is positive or negative when we do it with the ion filings. You can't actually distinguish that. So that's actually a good point. There was a question that says, when you say the charge falls off as 1 over r cubed, what is the value of r? And how would we measure when it falls off? Okay, what I say for the electrical dipole in this slide here is that the field falls off as 1 over r cubed, rather than the charge. The charge is always the charge. The charge on the dipole is this positive charge, and this negative charge. But their field, the strength of their field, the size of the field falls off as 1 over the cube of the distance from those two charges. So supposing I went a mile from these two charges, 1 over a mile cubed would be a very, very tiny number. We'd see a very small field. If I went 2 miles from the charges, 1 over 2 mile cubed would be a very, very small number. And so the field would be 8 times smaller than the field 1 mile from the two charges. And so the field falls off much more quickly as you walk away from the charge arrangement than it does if you walk away from a single point charge, a single positive charge or a single negative charge. Another question came in. On the slide, why doesn't it go from right to left? I'm not quite, so on this slide, the field lines, let me get my pen going again here. So these field lines emerge from the positive charge. They're coming out of the positive charge, and field lines are always coming out of the positive charge. And these field lines are heading into the negative charge. Field lines always head into the negative charge. So since the positive charge is on the left and the negative charge is on the right, the field lines sweep out of the positive charge and over towards the negative charge. So I hope that's okay. Okay, look, I've just overrun my time. We've got through the definition, the concept of the electrical field. We got through some examples of calculating electrical fields from electrical forces using the field equation, and calculating electrical fields using Coulomb's law and superposition principle. And we've just looked at how you sketch electrical fields, how you draw electrical fields. There's one topic I didn't get to, is the fields and conductors. I'll do that at the beginning of next class.